suggest we get started. I hope you enjoyed your lunch. We had already a very interesting presentation this morning about what Timbre is, and we're now moving on to more insights into how humans perceive Timbre from, I guess, a neuroscientific viewpoint. So it's my pleasure to introduce Professor Tim Griffiths. Thank you again for being with us today. Tim is a neurobiologist who studies normal and abnormal auditory cognition. He's a welcome senior clinical fellow, professor of cognitive neurology at Newcastle University, honorary principal at the Wellcome Trust Center for Neuroimaging, University College London, and adjunct professor at the University of Iowa. He also runs the Newcastle Cognitive Neurology Clinic, and he's talking to us about how do we perceive them.
Yes, thank you very much indeed, sir. It's a great pleasure to be here. And actually, about 10 years ago, when we first started getting interested in Timbre, I spoke to Steve McAdams about what a good idea it would be to set up a Timbre meeting. Anyway, it never happened, so I'm really pleased to be here. And actually, because it is 10 years later, I have a vague idea where to start. It is really a difficult problem. In terms of the question I'm speaking to today, how do we perceive Timbre? If I were French, I would answer like this. It really is that daunting because it's such a huge, complex aspect of perception that it's really quite hard to know where to start when you're looking at such sort of low-level measures as I look at, like blood flow and neural activity. But what I thought I'd do is just give you a couple of ideas about an approach that we're taking to Timbre. And I very much enjoyed the last talk before lunch, actually, and the idea that Timbre is a gestalt. It's something that we pull out, and I very much think of it as a cue to object perception in terms of real things in the sensory world around us. And what I'm going to do today is to talk briefly about a sensory framework for Timbre. Timbre is very much a percept. It's not an acoustic stimulus, although it is related to aspects of the acoustic stimulus, and it's not an acoustic stimulus representation, although it is related to aspects of the acoustic stimulus representation. It's very much an abstraction from those sensory properties, and before we can begin to understand Timbre, I think we need to have an idea about how the relevant sensory properties are represented within the brain. But I'm going to spend most of the talk talking about aspects of Timbre and how they are represented within the brain and how we might map out the network for Timbre perception. But I want to go beyond that a little bit as well. As functional imagers, we're often criticized for just defining lots of brain blobs. And quite a lot of what we're doing at the moment is actually trying to go beyond defining networks to actually defining systems for pitch and timbre and object analysis based on not just the network but the effective connectivity between aspects of the network and modelling using dynamic systems identification techniques, which you as engineers will know more about than I do. And finally, if there's time at the end, I'll tell you a little bit about how Timbre can go wrong. I'm a neurologist and I spend time seeing people who have congenital unacquired disorders of Timbre, of musical perception, but we occasionally see people with timbral disorders as well, and I'll say a little bit about that. So let's start with sensation and how the acoustic structure of the stimulus that's relevant to the to timbre is represented within the brain. As I said, timbre is not pitch, and it's a percept and not a stimulus property. Timbre is not pitch, and that's probably, as far as I can see, about the only point of agreement within the field. but it's a percept and not a stimulus property. And all of the syntheses of timbre seem to agree that there are properties that are more related to the time and to the frequency domain. So how are those fundamental properties mapped within the brain? Well, as you all know, we have representations of the frequency and time structure of stimuli from the cochlea upwards. And we've been looking at how these are mapped within the brain, both in the ascending pathway and within the cortex. I'm sorry, I haven't got a pointer today. I'm going to have to use the cursor. It's not urgent. These are actually bold data showing the blood flow response within the macaque. I could have shown you human data if we had any. We think that the human data is very similar. And what we've done here is to map the bold response as a function of the frequency that is presented to the subject and as a function of the modulation rate of the stimulus. Oh, thank you. You've got a...
Actually, I can't see laser pointers, so
Oh, right. You
could you use the mouse pointer?
Yeah, no, that's fine.
Right.
So what we've done here is obviously, as you know, in the auditory pathway, you go from the cochlea to the cochlear nucleus, up the ascending pathway to the inferior colliculus, to the auditory thalamus, and thence to the cortex. These are sections which you can see here, which are through the inferior colliculus, the obligatory relay within the midbrain of the primate. And what you can see here are maps of the frequency, the bold response as a function of frequency within those nuclei. So this is the back, this is the front, this is the right inferior colliculus, this is the left inferior colliculus. And what you can see represented here from red to blue is low to high frequency laid out in a systematic order. So this is tonotopy, which is a feature of all of the structures, all of the nuclei within the ascending pathway. So we have a systematic representation of the frequency structure of the sound. What we've also done in these experiments is to actually map these are narrowband stimuli that are amplitude modulated as well, and what we've done is to map the preferred amplitude modulation rate from low in red to high in blue. And what you can see here is a systematic representation which goes from low at the back to high at the front. There's a bit of maths on the right, but all the maths is showing is that those two gradients are not aligned. What you can see is that there is an orthogonal mapping of the frequency structure and the time domain structure of the stimulus within that same structure. So you can think of this as a sort of framework from which time and frequency properties might be abstracted. At the level of the cortex, things get more complex, as you might expect. These are maps which show it's actually the macaque, and the human auditory cortex is rather similar. So the human cortex is at the top of the temporal lobe on both sides, buried within the Sylvian fissure at the side of the brain. This is looking down onto the top of the auditory cortex. This is the left, this is the right, this is the front, and this is the back. And this shows basically how the preferred frequency changes along the auditory cortex. And essentially what you have in the cortex are multiple areas, each of which contain their own tonotopic gradient with reversal of the gradients between the different areas. So this is in A1, the primary auditory area, the gradient goes from high to low, and then there's a reversal in the area in front of that. And there are actually 8 or 9 areas on each side, each with their own different maps. So it's a much more complex mapping of the frequency structure of the stimulus. There's also a superimposed mapping of the time structure of the stimulus. So from, again, blue is high and red is low. And what you can see is as you move away from the primary auditory cortex, you see a tendency for areas to be more active as a function of slow modulation rates. put another way, I think this fits with some ideas that David Purple from NYU has proposed, that actually as you get away from cortex, there might be a preference for longer windows of analysis, which kind of fits in with ideas in the visual system, where as you go to higher and higher areas, you see bigger and bigger receptive fields. But all I'm trying to show here really are some general principles, and really to point out that even the mapping of the frequency and time structure from which the timbre is abstracted is already a highly complex problem. And what we're trying to do here is to try and get an idea about how timbre is pulled out from this fundamental mapped structure. So let's move quickly on to perception. Multidimensional scaling has been mentioned already, and these are data from Steve McAdams from more than 10 years ago now, where you're basically mapping differences in perceived timbre into a Euclidean space, where the physical difference within Euclidean space corresponds to the perceptual difference between those two instruments. And we've got some hybrid instruments as well here, which were mentioned before lunch. This is very much a perceptual technique, and obviously what various people have done is go back and say, well, what are the dimensions of this space? And there seems to be general agreement about a first and second dimension corresponding to the overall temporal envelope and the spectral envelope. In terms of other dimensions, I guess the arguments are going on with mentions of fine temporal structure like the clarinet that was mentioned this morning, with others emphasizing spectral flux. I don't feel particularly passionate about what the dimensions of timbre space should be, and in fact there's been recent interesting work from the group of Thea Unison and Tabitha Elliott, who's carried out further studies to actually twist the axes further still, and they've argued actually that all of the axes for timbre are composite, all of the dimensions rather, are composite dimensions in the time and frequency dimension. What we've been trying to do over a number of years is just to try and sort of deconstruct the perceptual space, not because we think we understand what the dimensions of timbre should be, but really just to try and get an inkling as to how this complex percept that is not pitch might be mapped in the brain. And the simplest way, and the first dimension I want to think about is spectral shape, or spectral centroid, comes out of the multidimensional scaling analyses. And actually one of the first people to look at this was Dave Green in the 1980s and onwards, in a body of experiments which were called profile analysis experiments. And they were quite simple experiments really, where you're looking at how you might detect a spectral shape. Here's a log space reference. So you've got a number of components there which are spread out in log frequency space, and then you might have one that pops out. Can you hear the single element popping out there? And what they did in these experiments, they actually roved the overall level of the sound, and so and when they do that, you can actually still perceive the single element popping out, which obviously can't be explained just by listening within one critical band. The other thing they found was that actually the more and more elements you had up to a certain limit across frequency space, then the more helpful that was in terms of improving your detection, which again can't be explained by listening within a single frequency band. And this, it's hard to believe it now, but they found this surprising in the 1980s, and when everything was explained by the critical band and by one particular frequency channel at a time. But this is clearly identifying a particular mechanism for spectral shape analysis. But these are hugely unnatural stimuli. Obviously, natural sounds come from sources where we'll have a shaped spectrum with a number of elements that change. And I had to train and train and train people to do these. So we did some experiments looking at spectral shape analysis to see if we could get at more sort of naturalistic stimuli. They still sound pretty artificial and not half as beautiful as the sounds we were listening to before lunch. But just to give you a bit of an idea, so here's a stimulus sequence where we're applying a spectral shape to a harmonic series, which is a bit like a voiced vowel, right? So this is the same vowel over and over again. We can change the pitch of the vowel. So despite the fact the pitch is changing, you can actually hear the similarity in the timbre of the sound. And the other thing we can do is to change the timbre and keep the pitch constant, which is a bit like a changing vowel. But what we're wanting to do in these experiments is actually to get beyond what might be the fundamental primary, as it were, absolute stimulus representation, to get at a form of abstraction that might be related to spectral shape. And we've done that by using these alternating stimuli, which alternate between a harmonic series and a noise carrier. So it's a bit like a voiced or a whispered vowel, for example. So this is where the spectral shape sounds the same. And despite the fact there's noise and a harmonic series there, you can hear a certain similarity between the two sounds. And then we can look at your ability to abstract the spectral shape over and above that fundamental. So really what we're trying to get at is how do you abstract spectral shape relevant to that dimension of timbre, irrespective of the fine structure of the stimulus. And we've looked at this with functional imaging, which you can see here. So this is again looking at the auditory cortex. STP is superior temporal plane. These are human data now, looking at the front and the back on the left and on the right hand side. Humans have a sort of fold in the cortex called Heschel's gyrus. But what you can see here is that when you change the spectral shape or the pitch of the harmonic stimuli, we see changes which are very close to primary auditory cortex, human homologs of core. But when we look at this contrast between the changing spectral shape and the fixed spectral shape, we see much higher order areas of auditory cortex which are involved. So these areas in blue are at the back of the superior temporal plane in human homologs of core cortex in monkeys. So it's a higher cortex, and this section here is actually much lower than the superior temporal plane. It's the superior temporal sulcus, and what you can see here is actually activity corresponding to that abstraction, which for the first time is appearing to be right lateralized as well. It's more on the right hand side of the brain than the left. We can go further than that though and actually look at whether the system rather than just mapping the network. And we've done this with a technique called dynamic causal modeling, which works like this. You can look at the time series of data from one particular area, from the different types, different areas, and what you do is you set up competing models which explain the activity in the three areas as a function of the effective connectivity between the areas, as it were the causal influence of one area on another based on neural connections. And you can also look at the modulation of that effective connectivity as a function of what the brain is doing. And obviously what I've just shown you is activity within the primary auditory cortex, within higher order cortex at the back of the auditory cortex, and in higher order cortex still in the superior temporal sulcus. So we have three nodes, and going from Heschel's gyrus, that primary cortex, you could get to the other two cortices in a parallel way, or you could go in a serial way to the slightly higher cortex, to the much higher cortex, in a serial way like this. And what we do is we evaluate these models one against the other. We carry out a form of Bayesian model comparison. And what happens then is that you end up with a winning model which best explains the data that you see. And this is the winning model. So this is Heschel's gyrus, the primary cortex. This is the planum temporale, the cortex at the back of the auditory cortex, and this is the superior temporal sulcus. So the winning model is a serial model where you go from primary or core to belt to parabelt, if you will. And what's shown by the red diamond here is actually modulation of the effective connectivity between the primary and the non-primary cortex as a function of that abstraction task that the subjects are forced to carry out. So I think what we're doing here is to try to develop a psychophysical paradigm to look at spectral shape analysis relevant to timbre, where the imaging and the modelling is suggesting a hierarchical mechanism. We've also looked at other aspects of other dimensions of timbre. I won't torture you with any more sound examples now, but this is a stimulus we've used for spectral flux analysis. Here we're putting random components in log frequency space here on the ordinate, this time on the abscissa, and can you see that the components are amplitude modulated as you go along? So what we can do here, when R is 0, this means that it's just a Spearman correlation between one time frame and the next. So when R is 0, there's no correlation, it's like a random sound. When R is 1, it's actually constant, so it's like a fixed sound. And in between, you have degrees of spectral flux, which we can systematically change. And we found this quite interesting. What we find is that when we carry out that manipulation, the primary auditory cortex is not interested, but when you go to the level of belt areas in the front and the back of the cortex, so these red areas here, which are in front of and behind the primary auditory cortex, we see activity which actually increases as R increases. Put another way, what we're showing is that the activity increases when the spectral flux decreases, or put another way, we're seeing activity that increases as the temporal window over which the change occurs is occurring. So we think this again consistent with the sort of suggestions from the experiments that we carried out with more deterministic amplitude modulation. And this is another stimulus which I made a few years ago after an argument with David Purple that you couldn't create form from motion in the auditory system. He was right, you can't, but it led us to use this particular stimulus for a number of timbre experiments as well. Can you see here what we have are frequency modulation ramps where we can constrain a number of them to be coherent as a function of time. The short version is that we see activity within the core cortex, within primary auditory cortex, which occurs as a function of changing from one object to another when the correlation changes, where the brain recognizes a rule change. But actually, in terms of the absolute correlation, which is the best correlative timbre that we have, we see actually much higher level activity corresponding to what the timbre is, which I think would roughly correspond to the arguments I was making about the other dimensions that we've looked at. So I want to move on a little bit from timbre, or perhaps move sideways from timbre, because I think both pitch and timbre can be represented as cues for object perception. And I want to say a little bit about pitch models. And a class of pitch models which we're developing now, which we're very interested to see whether might also apply to the timbre domain. And these are data from a neurosurgical subject that I've studied in Iowa. So basically, I'm the only neurologist in the world with any interest in the auditory system. Matt Howard in Iowa is the only neurosurgeon with any interest in the auditory system. So it's kind of inevitable we might talk to each other at some point and collaborate, and that's happened. And basically that group are the only group in the world to put depth electrodes into neurosurgical subjects along Heschel's gyrus. These are the contact points along Heschel's gyrus in one subject. And the reason for doing that is because you can then look down on the inferior medial structures within the temporal lobe to find out where the epilepsy is coming from. But whilst the electrodes are in, it also allows us to do serendipitous experiments to look for brain activity corresponding to different percepts. These are data which are time frequency plots showing the induced activity corresponding to the transition between a noise and a control and a regular interval noise, which is associated with pitch. And what this expanded panel here shows that in one of these areas is activity within the high gamma range between 80 and 120 hertz, which is oscillatory activity which corresponds to the presence of pitch, which is not present before the transition to pitch, and which we only see for stimulus rates which are above the lower limit of pitch. But the reason I wanted to mention this really was to point out this modelling that we've done, again using dynamic causal modelling. And when we do modelling, the actual neurophysiological data gives us much more defined time series from each of the areas we're interested in order to carry out analyses of the effective connectivity. And what we've done here is to actually extract the time series from the two core areas towards the so primary cortex, if you like, towards the medial part of Heschel's gyrus, and a non-core area in the lateral part of Heschel's gyrus. And what we found very interesting here is that we've looked at the connection strength between the non-core area and the core area as a function of the pitch strength. And from first principles you might think, well, as the pitch strength goes up, maybe the connectivity from primary to non-primary should go up. That does not happen, and we find exactly the reverse. In other words, as the pitch strength goes up, what we find is that the effective connectivity from the higher level cortex to the primary cortex goes up, but the effective connectivity from the lower level cortex to the higher level cortex goes down. And we think that this is consistent with a class of perceptual models that are based on predictive coding. And the idea is this. You have a higher level area that actually predicts what the percept might be. It projects to the primary sensory cortex. And what happens at the primary sensory cortex is there is a comparison between that prediction and the ascending information from the auditory system, so that what goes back up to the higher level area is not some kind of correlate of the percept itself, but an error signal corresponding to the difference between the prediction and the incoming information. You're engineers, I'm not. You'll appreciate that this is an extremely efficient way to run a railroad because it's actually a sparse type of representation, where at each level of the system you're only passing up what is wrong about the prediction coming down. So it's a very useful system. So what I'm quite keen to do is actually to go back and revisit some of these Timbre experiments that we did with Bold 10 years ago, and actually to look at whether this predictive coding account might actually account for aspects of Timbre as well. I'm going to very briefly, I've got 3 minutes. Yeah, I just want to finish by just saying a little bit about how the system might go wrong. As I say, we see people in the clinic who have disorders of mainly pitch perception, actually, and we've done a lot of work over the years on congenital amusia, inability to appreciate music, and acquired amusia after strokes. This was a patient I saw nearly 10 years ago, who was a television producer who did a lot of work with actors, and he was a keen amateur listener to jazz music, actually. Somebody's got to be. And he presented to us after he'd had a right hemisphere stroke, which had damaged the cortex on the right-hand side. His cochlear function, his peripheral hearing was normal. There was no new deafness. He did have some problems with recognizing music, and he had an acquired amusia. He couldn't recognize tunes like Happy Birthday, even, for example, which would previously have been very easy. But I think the striking and interesting thing about him, in contradistinction to a lot of the other patients that I've seen, is that he described a particular problem with perceiving the timbre of sounds. And he gave a number of examples. Voice timbre changed, so that when he was listening to people's voices, it would often sound like one of those old transistor radios, or if you hear people's if you hear people's earphones from a way away. So it's like a sort of tweeter function for the engineers here. So there'd clearly been some sort of spectral change in his listening to timbre. And he described an interesting experience when he went to a football match a week after he got out of hospital with his son. And he thought there were a lot of people holding up transistor radios in the stadium until he realised there was actually a lot of people around him sort of speaking and cheering and things. It was that abnormal, his experience. And so we looked at this in a number of ways. This is his brain lesion, and I won't bore you with the details, just to point out really that he's got a stroke which you can see in the right hemisphere, which is sparing the primary cortex, which is here in the medial part of Heschel's gyrus, and damaging the belt homologs in humans in the lateral part of Heschel's gyrus. He's also damaged the part behind, and this section here shows how he's damaged quite a large part of the superior temporal gyrus, which is the gyrus on which all the auditory cortex is based. And we did a large number of psychophysical studies on him. This just shows really that he can do basic psychophysics and he can perceive simple sounds normally. IRN is iterated rippled noise. This is a noise with regular structure which is associated with pitch, and his perception of that was normal. AM is amplitude modulation of a narrowband carrier at 2 Hz and 120 Hz, which is normal, as is his perception of frequency modulation of a narrowband carrier at 2 and 120 Hz. And that's just confirming the normality. He did have problems in the pitch domain, which were brought out by a battery called the Montreal Battery for Evaluation of Amusia, which was has been designed by Isabelle Peretz and colleagues in Montreal. But this was a thing which interested us, and we thought went some way towards explaining his timbral deficit. And what we're looking at here is his ability to detect the change in an M-shaped spectral envelope, which has been applied to harmonic series. We actually tried the more complicated experiment I showed you earlier, where you're trying to detect changes in an envelope applied to an alternating carrier between harmonic series and noise. He just couldn't do that at all, and normal subjects can. But this is showing that his thresholds for detecting spectral shape changes are actually double those of normal controls that we looked at. So I think this is consistent with the normal data I was showing you earlier. The argument would be that he's damaged the system beyond the primary cortex for the abstraction of timbre. And I started at the beginning by arguing that timbre, is a percept, and we are looking at these individual dimensions that I've called proto-timbre in a fairly arbitrary way, really. But what I find quite reassuring, really, is that despite the fact we're looking at such different dimensions, looking at the the spectral flux and the spectral shape, we are identifying a very similar system involving non-primary auditory cortex in the superior temporal plane and right lateralized cortex in the superior temporal sulcus. And beyond sort of getting at that network, I think, as I've implied, really, I'm very keen to sort of get more refined time series so we can better tease out what the network is in our neurosurgical patients. I'll stop there. Thank you.
Thank you very much, Tim. I guess we can go to questions. I suggest we do them spontaneously. I have some questions you guys put there in that document. We can use that in case you don't remember them. But, yeah.
So I'm really interested. So I read a book, and you might frown or not. I don't really know. Which is called On Intelligence. I don't know whether that's whether people who actually do research at universities like that book, because it's kind of a maverick guy. But he talks a lot about this up and down. What you call the sparse passing of information between high level and lower level systems.
Yes.
And I'm just very interested in that, and I hope you could maybe just elaborate a little bit more on that.
Right.
How that works.
Yeah. So I think it's it's like a lot of ideas in auditory neuroscience. We stole it from visual neuroscience, really, and it was Rao who first came up with the idea in round about 1990, and applied it to aspects of visual perception, and it does seem to be strongly supported by a number of aspects of visual neuroscience. In terms of the modelling, people have tried to look at more broad aspects of modelling and whether it might explain sort of more complex perception. So Carl Friston's very prominent in this field, and he's been looking at whether his group have data suggesting that predictive coding algorithms can be used to explain the mismatch negativity phenomenon, which is a high-level phenomenon where people might listen to repeated exemplars with occasional oddballs. One thing I'm interested in looking at, as well as just looking at basic perception, is whether predictive coding accounts might account not just for perception, but also for things like working memory, and how we hold a sound in mind for seconds. I don't mean phonological working memory that we use to remember telephone numbers, but just holding sounds in memory. And I think we're trying to tease that out at the moment. Actually, we've got some evidence that for working memory there is a particular involvement of the hippocampus and the inferior frontal cortex, and we're interested in whether there might be similar back projections from those higher areas, which might explain which might explain working memory. It's a little bit maverick, to be honest, in that it is very different to perception, in that we're looking at a mechanism that you might hold a sound in mind for seconds or tens of seconds, in contradistinction to a mechanism for just perceiving something over hundreds of milliseconds kind of thing. I mean, if anyone is interested in predictive coding in general, I think the best account, I have to admit I haven't read that book, I've only seen it in secondary sources, but I think one of the best accounts of predictive coding is in Behavioural and Brain Sciences, written by someone called Ian Clark, and it's quite good fun actually. So if any of you have read Behavioural and Brain Sciences, they'll have a sort of article to wind everyone up at the beginning, basically, and then about 15 responses to the article. So not only do you get Ian Clark's view, which I think is very trenchant, but you also get responses from a number of people in the field.
No one's wanted to ask a question. I've got another one. But happy to see. So I'm really interested. So I was working with Armand on the temporal evolution.